Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we are going to look at the potential step excitation in thin layers of solution. So far we have looked at different potential step techniques that were chronoamperometry, chronocoulometry, and then chronoabsorptometry, and all of them are analytical techniques, and you already know that they can be used to measure certain type of responses, and then from those responses we get some valuable analytical information. Now in this technique, which is potential step excitation in thin layers of solution, we are looking at something which is called thin layer electrochemistry, and this is a special area having some special advantages of restricting the diffusional field of electroactive species and products by application of barriers. For example, if we have a solution, then this solution is confined to a well-defined space, and due to that it forms a layer, a well-defined layer, which is actually having a very small thickness of around 0.2 millimeters that we will be looking at in forthcoming slides. Now this thick layer, this 0.2 millimeter thick layer that we are actually looking over here on our slide, which is also mentioned here like this 0.2 millimeter thick layer is confined or trapped between certain situations. For example, this layer can be trapped between an electrode and an inert barrier. That is, let's say that we have one side, so let's try to erase it first. Okay, so we have this option, that is, let's say that if we have something present like this, and let's say that at this part you have something connected, and then you have an inert block present on the other side. So the thin layer must be present between this space which is present between this block and then this electrode surface. So obviously previously we saw that electrode, if present, is let's say if this is electrode, then there is a long place over here, and then we have some bulk solution present in this space, and then the electrode surface have its immediate part, and then there are bulk of the solution. Anyway, but here it is not like that. So then it can be also a situation in which the thin layer is trapped between two electrodes like this, like for example like this, or something like that situation. So both of these are considered as electrode, and then it can be a thin layer which is basically present between two inert barrier like this, like for example these are two blocks, inert blocks, and between this a thin layer is present over here, and then an electrode can be present at any part like this. So there are certain conditions which can be applied, and in this way it can be, the thin layer can be present in different situations, and according to that, that is, it can be decided according to the experiment that is going to be performed. Solution that are trapped in porous bed electrodes, which are different from these ones, will have qualitatively similar electrochemical properties. However, they have their corresponding geometric complexities, which make this configuration of porous electrode not much useful when it comes to analytical applications. Then there is a variety of electrical excitation signals which can be applicable to thin layer electrochemical work at large. So we already know that this potential excitation that we apply is also quite variable in terms of responses and give certain information, as we saw in chronoamperometry and coulometry. So that type of variation is already present, and then we also saw an additional advantage in terms of chronoabsorptometry. So what we see is that the solution which is under study can be confined in different situations. Now, when we have this situation, that is, when the solution is confined, then we can look forward to certain type of diffusions that could take place, and that has already been discussed previously in lectures. So you should actually go and revise that. Now, the solution which is trapped in porous bed electrode can be actually giving same type of situation for same type of electrochemical response, but you can understand that since the surface can be variable, so the response will not be that useful, as we already discussed. Now we can have a look over here. For example, this is a kind of porous electrode which is present. So you have a counter electrode, then you have a reference electrode, and then there is a porous bed in terms of electrode, and the same is given in another type of view through which the electrolyte is flowing. Now you can understand that, let's say that there are pores which are present, elongated pores. So obviously this pore is metal on both sides, right? This part is metal and this part is also metal, and then this is the pore through which the electrolyte is passing. So this thing, which is the L, is the length which is from here to here, that is the pore length, and you can see that the pores will be distributed over the whole surface and forming a kind of bed through which the solution will be passing. So that kind of situation actually gives some irregular type of response, but still, since the solution is present or confined between very small spaces, that is these type of spaces, so therefore we can say that the response due to the formation of these thin layers inside these pores can give you a response which is somehow equivalent to thin layer electrochemistry, yet it is not much usable for analytical work. Now, in this kind of situation, we must know that these pores are very small in size when compared to the size of the electrode, and their overall volume be much smaller as compared to the size of the electrode. Now if we move forward, here we have a view of barrier that are applied. Here we can see that in A we have this electrode present over here, and then we have this barrier present over here, and then there is this distance between this electrode and the barrier which is given by L, and between this distance solution is present, and this solution obviously consists of initially, that at zero time, it consists of all the concentration of the oxidized species, and there is no concentration of reduced species present. And when the potential is stepped, for example, if we have this graph as we were studying, so that is at some initial time t is equal to 0 and t is equal to some time t, if we, I think need to clear it. Okay, so the potential is, that is E, let's say it is EI, and then at time it is stepped, and then it moved like this. Okay, so this is step, and let's say that at this point it is EF. Once it is stepped, it means that all of this oxidized species which is present over here should be converted into the oxidized to the reduced species, that is due to the stepping up of the potential. And now if it is enabled and it allows us to step it to another potential which is the final potential, then it means that at final potential this species will be converted back into the oxidized species. Now for this system we have, let's say if there is some diffusion of oxidized species. Now what we should remember, that there is no bulk over here. Okay, so this solution is a very thin layer which is confined between the electrode and the barrier. There is no bulk over here. So what we see is that the diffusion constant for oxidized species is equal to a diffusion constant for the reduced species, and both the diffusions are equal to each other. So all of the reduced species will be converted back to, let's say, oxidized species under the circumstances, and the oxidized species can be converted into reduced species. So if you step the potential again or back to initial potential and then to final and then to initial in a cycle, then this cycle of conversion can continue for a very long time. So what we must note over here, that there are some similarities in this type of situation and the situation that we earlier encountered, that is when the bulk is present. So what we see is that the response that we note over here is quite similar to the bulk response until or unless the potential actually, until it go and strike the barrier. Now if at any time the diffusion is stepped back to a value where the reduced species can be converted into oxidized species, that is at a rate controlled by this diffusion constant, which is equal to the oxidized species diffusion constant, then this situation that we see will be restored. That is, it will go back to the oxidized species. Now for this to happen, the species that we are actually using must be very stable species, and the complete conversion of one species into another will be only possible if we have both oxidized and reduced species very stable and are not breaking up into any other products. Now let us consider the same situation in another way, that is, if we have, instead of potential, if we are if we note the response in terms of time as we actually noted earlier. So in terms of that response, we see that here is the current, which is very typical for a double layer, that here the current is coming back and then it is striking a barrier, and then it is going back to form the other species, the oxidized species. So what we see over here is two type of responses. One is the normal chronoamperometric response, that is, this one is when we are looking at the bulk, and this one, that is the solid line, this is when we are looking at the looking at something which is acting against a barrier. So we see that at this point it start to separate, that is start to separate from the bulk behavior, which is given like this, and the effect of boundary is very visible over here. Now if this response is integrated to get a charge, so we see that again here we have a separation between the responses, between the two responses, which is one which is coming from the bulk and the one which is coming from the response from the barrier when it strike a barrier. So this barrier is actually a diffusion barrier which is placed there, as we initially said, the diffusion barrier, so that there is no bulk available. So this can be mathematically written in this form. So here we see three equations over here. One is for the current, and the current, when we take the derivative of the concentration profile, which is over the distance, which is this term, then we get this equation in which this P is defined as this term, and you can see that it is including the area of the surface of the electrode and the diffusion constant, which is replaced over here. Now this is a tricky process and we don't need to get into the detail of this, but however this is what we get for this type of situation. Now if we integrate this, we can get charge, and for charge we get this kind of expression, that is, if we integrate that under the time 0 to t, that is the time in which the step was taken and then was maintained, and then when the step was reversed to a final potential and the current was noted and then converted into a charge. So this is again this equation that we get over here. Now if we take this, if we change this limit to infinity, then what we get is the Faraday's law, and you can see that this is the Faraday's law over here. Here we see an important term, that is the Q infinity, which is quite important and can be used to calculate many things. Now this Q infinity can be used to calculate number of electrons, then it can be used to calculate the concentration, bulk concentration of oxidized species, the initially, which was, or it can also be used to calculate the volume, and therefore it is an important term. Now in the thin layer, now we are getting a lot of information here. For example, we are getting the number of electrons, and once we get the number of electrons, it can help us to elucidate or understand the mechanisms that are taking place. Then in addition to that, the other advantage that we have over here is that the volume of the solution that we are using is very small, since it is a thin layer, and this thin layer is of very small thickness. So the volume of the solution that is used is of the order of 10 microliters or around that. So again, this is another advantage. In addition to that, it can give us a characteristic time constant for the theoretical response, and which will tell us that when the electrolysis process can be completed to a certain value. So it means that it will tell us that 1/2 the mean time of molecule to diffuse across a certain length, and this can be then used to calculate many other parameters. So it is giving us information about the kinetics, about the electrochemistry of the system, and also about some information about the electrodes. A typical example of such reactions that are encountered in thin layer processes, for example thin layer coulometry, will be to determine the value of number of electrons involved when we apply this technique, or as thin layer coulometry to chloropromazine. So a thin layer kilogram of oxidation of chloropromazine by a potential step of 575 millivolt versus a saturated Coulomb electrode can be looked upon over here in this figure. And what we see is that a potential step is repeated in a supporting electrolyte, and that can be seen over here. And what we get over here are these important parameters. By extrapolating this linear part of the curve to the y-axis, where we are getting the value of qt, and then if we extrapolate this part, then we are getting the value of qb. So in other words, we have measured the total charge and also the background charge, that is qt is the total charge and qb is the background charge, just by extrapolating the response that we are getting. So why we are extrapolating? Because it will give us the value of charge for these for this system at 0 time. Now the difference in qt, and that is the total charge, and the background charge, will give us the Faraday charge from which the value of the number of electrons involved can be calculated. Now for this kind of experiments, we can see that this is quite a simple experiment. So what we do is that the thin layer cell is pre-calibrated, and the volume is also carefully chosen, and after carefully choosing a volume, we pre-calibrate the cell according to that volume. Now for this pre-calibration, some standard can be used, and then by comparing to the standard, the response can be also standardized. So in case of chloropromazine oxidation, we get 1 electron for the oxidation of chloropromazine. Now if we have ideal conditions, then the charge consumed by the double layer capacitance and adsorbed reactant will follow the same time course as is discussed for the coulometry earlier in the previous lectures. It will not be different, but obviously if it is not ideal situation, then it will not happen. The reason is that the ratio of electrode area to solution volume is larger for thin layer experiments, and the charge account for may represent a much greater proportion of the total charge. So this actually help to take advantage of restricted diffusion experiments and help us to understand the surface phenomena. Now the same thin layer approach can also help in spectroelectrochemistry, because since it is a thin layer, so it means that the absorption the absorbing response can be more easily and more accurately calculated, and there will be better spectral observation without interference from the starting material, because the concentration the thin layer will determine that the path length will be small, and therefore the absorbing species will be responding more abundantly. Now the stability of the product species can be also assessed spectrally or by comparing the background charge and the QF at various switching times. So there is some advantages of using these type of techniques. Now in thin layer cell there is rapid diffusion mixing, for example. So what we observe is the rapid diffusion mixing. So what we see over here, that initially we have this situation over here, that is we have the concentration of the reduced species and then the concentration of the oxidized species, and this is the distance from the electrode, and here is the barrier. So as you know that both of the species are very stable, so if we interrupt the experiment and disconnect the supply, so the two species will actually get to a certain concentration in a matter of a very small time or instant, and this is due to the rapid diffusion mixing which is observed. That is, this one is the again initial condition, and we have this condition that this R is giving this solid line and O is giving the oxidized species, that is this dashed line. So here the relaxation process is taking place, that is the concentrations are mixing among each other due to diffusion, and after some time these concentrations become constant and there is no more change in them, and this process is taking place rapidly. The same if done in the experiments when we were looking at the bulk solution, that is at the semi infinite condition, then this process will take a very long time, that is when the concentration of the reduced and oxidized species will become stable, that is they will get to an equilibrium. It will take quite a long time, but here since the diffusion mixing is very fast, so therefore it just happens in a matter of instant and doesn't take a very long time. Now due to this speed, we can actually use the same technique to measure intermediate. The example of such reactions is the oxidation of 5,6-diamino uracil, in which an intermediate is formed or generated electrochemically, and then spectroelectrochemistry is used to determine the rate constant for this electrogenerated intermediate, which is formed electrochemically. So this can be clearly observed over here. This is the formation of intermediate, electrochemical formation of intermediate in this reaction over here, as you can see, and afterwards this is observed spectroelectrochemically. Now this is what is happening to determine the rate of this formation of intermediate. So a thin layer chronoabsorptor colorimetry experiment can be set up for this determination, and for this we actually monitor this intermediate at 330 nanometers, and this is shown over here. So you can see that there is increase in absorbance, and then it is decreasing with time. So thin layer chronoabsorptometry of electro-generated reactant in an optically transparent thin layer electrode. Variation of the absorbance of the intermediate species during the electro-oxidation of 10 millimolar 5,6 diaminouracil in McKelvin buffer at pH 5 and 0.35 volt. Now the arrow here indicates time at which all 5,6 diaminouracil has been electrolyzed, and the B show the kinetic plot of time versus the absorbance at 330 nanometer of intermediate species. Absorbance data is taken from this curve over here, and the setting time is equal to 0 at the point where the concentration of diaminouracil was 0. So from here we get a rate constant value for this over here, which is 7.6 into 10 raised power minus 3 per second. So anyway, now there is another application, that is, it can also be used for the study of o-tolidine in aqueous acidic solution. And the absorbance, that is the experimental spectra of this experiment, is given here, and you can see that how is that proceeding. Starting from here, it is going like A, B, C, D, E, F and G, that is species of A3, then A2, then A1, and it is proceeding. For this study, a specialized electrode is used, which was already mentioned, that is let's say optically transparent thin layer electrode is used for this type of study, and when the experiment is performed, the curve is recorded after application of 0.800 volt, that is 0.800 volt is applied, and this causes complete oxidation of tolidine, and we say that the concentration of the oxidized species to the concentration of reduced species is much greater than 1000, which ensures the complete transformation. So in that case, this curve, that is the last one, is recorded, which shows that all of the species is converted to the required product which was needed. Now the intermediate spectra correspond to value of the E